Section 6 is on rational functions and asymptotes. Um, to keep it real simple, a rational function is when we have a function that's made up of a fraction of other functions. So probably the most basic one that we can talk about is y equals 1 over x. That is that is considered rational. And it's the most basic one, as I said, because it's just simply 1 over x. So what we'll do to graph this thing, to give you an idea of what the graph is going to look like so that you understand it a little bit better, we'll look at some values. One of the values, when I look at 1 divided by x, is if I look at the x value of, say, 1, or negative 1 for that matter. Well, if x is 1, 1 divided by 1 is 1. And if x is negative 1, 1 divided by negative 1 will give me negative 1. So I can plot these 2 points. And those are really the only 2 very nice points on here. I shouldn't say really the only 2, but now what happens as x gets bigger? Well, the bigger the x value gets in the denominator here, the smaller the fraction value gets, the function. For example, if x is 2, I can pencil it in here. If x is 2, then I have the value of 1/2. But if x is, say, 10, well, then I have 1/10. And we can see that, all right, at 2 it's 1/2, at 3 it's 1/3, and so on, and closer and closer and closer forever. And if we make x positive infinity, there's still going to be some very small value there. But what happens in between 0 and 1? Well, first of all, we should notice that this cannot be 0. So right now we know that at x equals 0, which is the y-axis, this graph does not exist. That's called an asymptote. But what happens as x gets very close to that? Well, the smaller that the denominator gets, the bigger the fraction value gets. So as x gets closer to 0, the smaller the x value gets, the bigger the function value gets. So I'm going to attempt to draw this here. Let's see if I can do this and make it look somewhat reasonable. It's going to curve. It's never going to touch the x-axis here either. It's going to continue on forever, getting closer. My graph doesn't look like it, but closer and closer and closer and closer without ever touching. Now the same thing will happen over here, except it'll be the opposite way, because these are negative values. So the closer it gets, the closer we drop off to negative infinity there. For example, if I take negative 10, I have 1 divided by negative 10, which is negative 1/10. That's very close to the x-axis here. So I have basically 2 asymptotes. I have the y-axis. We will call that the vertical asymptote because it goes vertically. And we have the x-axis. The graph never touches that either. That is the horizontal asymptote. Now there are such things as diagonal asymptotes too. At first we're just going to talk about the vertical and the horizontal. So the basic thing about an asymptote, if you do not already know, we should know that an asymptote is a place on the graph that the graph does not exist, basically. All right. They are imaginary lines running in different directions that the graph can get very close to it, but it never actually reaches that value. and that's what an asymptote is. So what we'll do here is we'll look at a few different things, and we'll show some rules or some general guidelines that are helpful in finding where the asymptotes are located for any particular graph. That is, if the graph is a rational function that has asymptotes. So here's our breakdown for where we will find asymptotes. Okay, we defined what asymptotes are. The vertical asymptotes are going to be located anywhere that the denominator is equal to 0. We know that we cannot have a 0 in the denominator. The x values that make that happen will make this function not be able to exist. So we cannot have x values that result in the denominator equaling 0. Wherever that occurs, we will have an asymptote, a vertical asymptote, because the x value will not be able to equal that value. For example, if we look back at our graph from back here, the denominator cannot be 0. So x is a no-no. These are the x values right here. Just a reminder, sometimes we've got to point that out to make it stand out a little bit more. Oops. One more time. There we go. These are my x values. So x cannot be 0. That's what results in this line, the y-axis, the y-axis being the vertical asymptote. The horizontal asymptotes occur one of 3 different ways. Well, one of 2 different ways, really. And let me move this up so we can see the rational function here. This first condition says that if n is less than m, basically, if my 2 functions on top and bottom, if the top one has the highest power of it, its lead coefficient, if that number is less than this number, then y equals 0 is automatically going to be our horizontal asymptote. That was the case back here. This is a power 1. This was a power 0. We didn't have any x's up there. Okay, so we had the case where the top is the lead coefficient is a lesser power than the bottom. So that gives us the x-axis here as our horizontal asymptote. Second condition is if the powers of the numerator and the denominator, if the highest powers are equal. 5x squared plus something, 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 something over 2x squared plus something, something, something. They both have a highest coefficient, lead term with the highest exponent, x squared, let's say for instance. Then the fraction that you get by taking the lead coefficient here over the lead coefficient here is going to be where the asymptote is located. I'll give you an example of that in a moment. And the last one, if n is greater than m, that means the numerator is a higher powered polynomial than the denominator, then there is no asymptote. We can do long division and simplify it that way. But there are no asymptotes in that case. So here are 3 examples. You'll be asked to find all horizontal and vertical asymptotes for the following rational functions using this breakdown right here. So what you might want to do if you have this, you pause the video or whatever to copy this stuff down in your notes so that you can look at this while you're trying these problems. And pause the video and try and determine where the vertical and where the horizontal asymptotes are. And then resume it. First one I will look at, first I'll look at the vertical asymptotes. We know that the vertical asymptote will exist wherever the denominator is equal to 0. Well, I got to set this equal to 0. I notice that I don't think this factors. Let's give that a shot real quick, see if it does. And after looking at that for a bit here, it does not factor. So what we're going to do We can always solve, that's a quadratic, so we'll solve that using our quadratic formula. So we have the opposite of b. Oops. Okay, the opposite of b, plus or minus the square root of b squared, which is 25, minus 4 times a times c. Everything divided by 2 times the a value. So this becomes 5 plus or minus the square roots of, let's see what that is, 25 minus 4 times 3 times 1 is 13. All divided by 6. So we're going to get our 2 decimal answers. That'll be fine. The square root of 13 is not a nice number to deal with here. So we'll type in our 5 plus the square root of 13. I'm going to double up the parentheses here so I can do this all in one shot. Insert a parentheses here. So the numerator is all in one parenthesis there, and I'm going to divide that by 6. So there's one answer. The other answer I'm going to get by replacing the plus sign over here with a minus sign. So those are my 2 locations where there will be vertical asymptotes. One of them will be at x equals 0.23. The other one will be at x equals 1.43. So we'll document that over here. So we said about 0.23 and at about 1.43. Okay, there'll be 2 of those. For the horizontal, I should have given myself more room here. We might have to move these problems. Well, the horizontal, we got to look at the exponents here. The top has a power, the highest lead power, that is less than the bottom. So if we look back here, what does that tell us? If the top is less than the bottom, then y equals 0 is the asymptote. So I know that this will have a horizontal at y equals 0. And that's number 1 here. Okay, what I'd like to do is demonstrate that that's true. And we can just type in real quick. If I hurry, I'm going to pause this so I don't run out of my 15 minutes, and I'll resume it once I get it ready. Okay, so I have this graph typed in, this function rather, this rational function typed in. I have set up a viewing window. That seems to work pretty good, and I'm looking at the graph. Now this one, you got to realize your calculator cannot draw the invisible line or the dotted line like we can. So these spaces right here and here are the vertical asymptotes, and we said that those were at 0.23 and 1.43. So I'll use the trace feature here to show you that is true. If I just go back, you can see the cursor jumps. Okay, right there, it's at 0.19, and it's negative. And if I click one more spot to the right, it jumps to the positive side at 0.25. So that's at least evidence that this is correct, without getting too technical here. And if I go over here, notice I'm getting really close to 1.43. And it's negative 17 right now, so the cursor's down here at 1.40. One more click, it jumps to the positive side at 1.46. So there is a void at 1.43. That does demonstrate that. Now you can also see here, if I make the window go out further to the right, it'll make it a little bit more clear that there is a horizontal asymptote right here. I have to stop this video. I'm out of time.